Okay, in lesson 9.2, as you can see, we're talking about angles and angle measure. And eventually, before we're finished with this lesson, you will know how to draw and find angles in standard position. You'll know what the standard position is referring to. And then toward the end of this lesson, we'll talk about converting from degree measures to radian measures. You'll understand hopefully what this means. What is a radian measure? And you will also be able to convert from radian to degrees. So you should be able to go back and forth between those two different ways of representing the measurement of an angle. Just remember, you've probably had some basic geometry, or maybe you've had the geometry class, but we're talking about an angle as the basically the intersection of two lines, and it's the space near this point of intersection. We're talking about what is this space, how far apart would be this space, which would be these two lines that are intersecting at a particular point. And most of the time that's in degrees, but we're also going to talk about it in terms of radians, which may be something a little bit new for you. First of all, let's talk about some problems that will be like your homework problems. So your first block of problems, 11 through 18, these are the instructions. You're to draw an angle with the given measure in standard position. So for all of these problems, 11 through 18, you'll need to draw, it doesn't have to be anything fancy, but just make a couple of lines to represent the x-axis and the y-axis. All of these will be drawn on a little coordinate plane. You don't need graph paper for this. Nothing really to plot, but here's how we draw angles in standard position. It starts with putting your pencil always on the positive x-axis. So I'm talking about this part of your xy plane that you've drawn on your paper. So this line that I've drawn for the angle that we're about to draw, and this will be true for every angle, whether it's positive or negative, this positive x-axis is called the initial side of the angle. The initial side. Remember, there's two sides involved. And so starting here, we call this the initial side. And if we're going to draw a positive angle, like we are going to do here in letter A, positive 140 degrees, we're going to travel in a counterclockwise direction. So we're going to start going upward and around for positive. When we get over to letter B, and we'll do that in just a second, we'll start on this positive x-axis, the initial side, but we'll travel downward and around for negative. Okay, so every angle has an initial side, and then the other side is called the terminal side. So we're going to position the terminal side, and then we'll show the angle represented as 140 degrees. Well, if we travel from the initial side to this positive y-axis, you probably recognize that as being 90 degrees. All right, so let's just go ahead and go around first and label the terminal side. These are actually called quadrantal angles, where the terminal side is actually part of our coordinate plane, either the positive y-axis or the negative x-axis. This angle formed from the initial side all the way over to here, this terminal side, that would be 180 degrees. That would just form a straight line. If we started at the initial side and we traveled positive all the way around to this, which would be the negative y-axis, this would be 270 degrees. Just think we're adding 90 each time, of course. So I went 180 plus another 90, and I'm at 270. If I start at the initial side and I go all the way around, this initial side started at 0 degrees when I didn't go anywhere. If I travel a complete circle, of course, that's 360 degrees. All right, so again, if I stopped at any of these, either the x or y axes, these are called quadrantal angles, and quadrant means exactly that. These are the angles that are formed as a result of our 4 different quadrants being made by these lines that break our XY plane up into these 4 quadrants. Okay, so how do I draw 140 degrees? Well, again, I start here on the initial side, and I'm going to travel in the positive direction, which is counterclockwise. I'm going to go to 90, and then 140 is basically in between, of course, 90 and 180. If I did 135 degrees, that would be exactly halfway between. All right, because remember, in between here, this is, of course, 90 degrees total, and half of 90 is 45. So if you do 90 plus 45, you've got 135. And so 135 would be exactly right in between these two. So 140 needs to be just a little bit beyond that. Now, this doesn't have to be exact. You don't have to have a protractor and measure it out and do exactly 140 degrees. This is going to be your best guesstimate. And it's just going to be drawn out like this. It's a sketch. And as long as you're in the neighborhood, now if you went all the way around and you made it really close to 180 degrees, then that obviously wouldn't be right. So it should be in a relative positioning that looks like 140 degrees. And then another very important part of this is you need an arrow extending from the initial side to indicate the proper direction. Okay, so this indicates that we went in a positive direction. And so you're showing the initial side, the terminal side. Let me just label this. You won't have to label this every time. I just want you to be familiar with these terms. All right, the initial side is where you start, and that's always the positive x-axis. The terminal side is the other line that you think will represent the 140 degrees, in this case, made from these 2 lines. And this is, of course, the point of intersection of those 2 lines. All right, so don't forget, draw me an arrow. If it's positive, it's a curve that will indicate counterclockwise. And so let's jump over here and do the negative example. All right, so once again, I've got the initial side here. And for a negative direction, I'm going to go in the other direction. I'm actually going to go clockwise. And the way the quadrantal angle's set up for negative is this would be negative 90 degrees. Okay, and then I go this way and I'm at negative 180 degrees. This is negative 270, starting at the initial side and going 3/4 of the way around, and then all the way around, of course, in this direction would be negative 360. Okay, so for letter B, I'm supposed to draw negative 60 degrees. Well, that's about 2/3 of the way down to negative 90, and I'm just going to say it's right there. And I don't want to forget a little arrow. That's very important because that tells me that you understand the direction of a negative angle. And that would be it. I've got the initial side, the terminal side. I've guesstimated where I think negative 60 degrees is. And so that's really all there is to it. Not too bad. Okay, let's work on letter C. Here I am again, the initial side. And for 390 degrees, well, remember, positive means I'm going counterclockwise, or you can always think positive. You start upward and you work your way around. So this would represent 360 degrees. Okay. Well, I'm supposed to go another 30 degrees more, which is, you can think of 30 degrees as being 1/3 of the way within this quadrant. This quadrant is a total of 90 degrees, so I need to go another 30 degrees, so I'm going to estimate that to be about right there. And I draw my arrow to indicate the direction, and so this would be 390 degrees. All the way around, 360, plus another 30. Okay, let's do the same thing with negative 105. So here I am Initial side, always positive x-axis. I'm going in a negative direction this time, so I'm going clockwise. If I went to here, that would be negative 90, but I need to go a little bit further, another 15 degrees, so I'm not going to go too far. I'm going to estimate that to be about 15 degrees, and that's it. That's all there is to it. So just be careful that you give me an arrow. Some people will just show me the two lines, but I don't know for sure if you meant to go in a positive direction or did you mean to go in a negative direction. So your arrow indicating positive or negative will be an important part of your answer. All right, so that's what you will do on these problems 11 through 18. Draw your own XY lines, axes, and then show me what you think these angle measurements would be with your curve indicating positive or negative direction. Okay, so part 2 of our notes will help you with 19 through 24 of the homework assignment, and this is an exercise on coterminal angles. And that term probably makes sense to you. Coterminal, we'll just go ahead and define it here. Coterminal angles are two or more angles in standard position. And standard position means that the initial side is always the positive x, and then there's a terminal side. But with coterminal angles, two or more angles in standard position with the same terminal side. Okay, so let me explain this. You don't have to draw your XY plane, but I'm going to do it for this first one just to illustrate. Let's just imagine that we were asked to draw the angle 25 degrees. You're not asked to do that here, but let's just do it for illustration's sake. I'm going to say 25 degrees looks something like this. Okay, that's the positive direction. Now, if I were to travel all the way around, I would have another angle with the same terminal side, but it would be a completely different measurement because all the way around is another 360 degrees. Okay, so let me just do it like this. If I started here, initial side, I went all the way around plus another 25, these two angles have the exact same terminal side, and that's what it means to be coterminal. They're obviously different measures. This is 25 degrees. This is 385 degrees because I went all the way around 360 and then I did another 25. Okay, let me do another example in the negative direction. If I go this way, okay, and I stop at that same angle, okay, that same angle, but I went in a negative direction. Well, now I've done 25 minus 360. Same terminal side, and that's what it means to be coterminal. All right, two angles, they have different degree measures, but they actually have the same terminal side. All right, so you don't have to draw this. I just wanted to illustrate. Here's how you can come up with both a positive measure and a negative measure for angles that are considered to be coterminal. They share the same terminal side. So I'll just erase my little graphs here. This is really pretty easy because when we went all the way around in a positive direction, it's like we did this. We started at 25 degrees and we added 360. That's like starting at 25 and going all the way around. So when we do that, we get 385 degrees. So that would be an example of an angle with a positive measure that's coterminal. And if I do that same 25 degrees and I go the opposite direction, 360 degrees, then this will give me the angle with a negative measure. So you can just grab your calculator and do 25 minus 360, and you'll get negative 335 degrees. And so you're just going to basically do this same exercise, but hopefully seeing those graphs help you get a little better picture of what these angles actually look like. Okay, so for letter B, just think of starting at 175 degrees and going all the way around. You will still be on that same terminal side, but obviously you're going to be at a completely different angle, and this will be the positive measure. So you can just grab your calculator and do 175 plus 360. That's going all the way around, one revolution. That's 535 degrees. And if you start at 175 and you go the opposite way, 360 degrees, this will give you the negative measure of a coterminal angle for this angle. 175 minus 360 is negative 185 degrees. All right, so let's see about negative 100 degrees. Okay, the angle that's coterminal to it, if you start here and you go one circle all the way around, that's like adding 360. This would be the positive direction. That's obviously 260 degrees. And if you started at negative 100 degrees and you go all the way around in the negative direction, that will give you a coterminal angle with the negative measure, and that's negative 460 degrees. So the big takeaway from these problems is I just want you to understand what it means for angles to be coterminal. Two angles with different measures, but they share the same terminal side. And that's going to be important as we get deeper into Chapter 9, this idea of angles that are coterminal. All right. Okay, we're in part 3. And this is hopefully going to help you with problems 25 through 30, but before I jump right into formulas that you're going to use to do these problems, I want to stop for a second and provide a little background on this idea of radians. I get some students who, they know how to come up with the formulas, they know how to use the formulas, but they wonder, what in the world do we mean by radians? Degrees are pretty common. We've been looking at angles that have a certain degree measure. We know how these look in relation to, on our XY plane, we can guesstimate where 25 degrees is and 175 degrees, but this idea of radians is probably a new concept for many people. So bear with me for just a minute. I'm going to provide a little bit of background information on why we use the word radians and what is that referring to. Well, I'm going to start with a little discussion of pi. I find out also that students understand the decimal equivalent of pi that we typically use. Obviously, it's got an infinite number of decimal places after that, but typically we say the decimal equivalent for pi for calculation purposes is 3.14. Why do we use 3.14? Where does that come from? Why does your calculator know to use this decimal whenever we hit the pi button? Well, maybe you know this already, maybe not. I find a lot of students don't know this. Let me illustrate it this way. This is a good way of illustrating it, and you can do this at home using any kind of circle, maybe an actual pi, P-I-E, pan, anything that's a complete circle. But I'm going to use this circle to illustrate. I'm going to pretend like I've got this piece of string. So my red line here is a piece of string to represent the diameter. Remember, diameter means the distance right in the middle of the circle that extends from one side of the circle to the other. So pretend like this piece of string here is the diameter of this circle. Well, the diameter, if we take this piece of string, okay, pretend like this is a piece of string. I'm going to pick it up and I'm going to set it down. I'm going to stretch it out across or along the outsides of this circle. Okay, and if we were doing this in real life, this would be the way it would look. All right, let's say that I laid the piece of string down and I started it here. All right, so here's my string. I pick it up and I just lay it down on the outside of the circle, and it would extend probably to about right there. All right, so then I get it again and I lay the end of it where it stopped the previous time, and I lay it down on the circle again, and maybe it extends to about right there. Okay, so then I pick it up again and I put the end where it stopped previous time. I stretch it out on the circle, and it would probably end about right there. So where do we get this number for pi? Any circle you want to do this, it really doesn't matter the circle. If you take the exact diameter and you were able to lay that diameter along the edge of the circle, we call the circumference, it would cover the circle 3 times plus a little bit more. Okay, I'm going to call this the 0.14. It would almost cover it exactly 3 times. It would come short just a little bit, and I encourage you to do this little experiment. It's pretty neat. A lot of people just take for granted pi is 3.14. Why? Well, this is a good illustration why. This diameter will fit along the outside of this circle. It will lay along the outside of the circle 3 complete times with a little bit extra left over, and that's where pi comes from. Okay, well, let's take then half a circle. All right, so let's just imagine that we have just half of a circle, which means I've got, instead of diameter, I've got a radius. Okay, radius is just half of a diameter. All right, so you'll just have to pretend, I can't erase my circle, but just pretend like we're only dealing with half a circle, since I'm only dealing with half of the diameter, which we call radius. Well, if I took this radius length and I did the same thing, stretching it out across the circle, this, let's just imagine this is a piece of string. I lay it out and it would take 1, it would take 2, it would take 3, and then there would be just a little bit more. So I'm going to say that this is the exact half of the circle. All right, so this part is gone. Okay, I take the radius, I take this piece of string representing the radius, it's exactly halfway. It's the center of the circle that extends to the circle. I pick it up and I stretch it out, and it will lay here. Okay, 1 time I pick it up again, it lays here. 2 times I pick it up again, it would lay here. 3 times, and then the part that's left would be the 0.14. All right, so what is 3.14? It is pi. All right, so here I've just illustrated that halfway around the circle, according to my radius, would be the same thing as pi. It would extend 1, 2, 3, and then just a little bit more, which we already established is 180 degrees. Okay, well, let's just take half of the half. All right, so here I am. I'm splitting my half circle into another half. All right, so here I am. I'm dealing with the half circle. Well, here I've made a 90-degree angle, of course. What is that in terms of pi? Well, if halfway around equaled 1 whole pi, then this would represent pi over 2, or half a pi. Okay. All right, what if we split this in half? Okay, we took halfway around, or in other words, 45 degrees. All right, so in other words, we're doing half of pi over 2, or divide pi over 2 by 2, and you get pi over 4. Okay, if you come over here and split this in half, this would be 135 degrees, 90 plus 45, but in terms of pi, you know, remember all the way around is 1 pi. This is a fourth of pi. This is a half of pi. This then would be 3/4 pi, or we would say 3 pi over 4. And then that would take us around to 1 pi. Okay, so here's the idea behind radians. Radians means that if I take my radius as a string and I lay it on the outside of my circle, let's say it's the number of radiuses, which is not a good word, the number of radiuses that it would take to represent this particular angle. All right, so in other words, if I pick up my radius as a string and I lay it down, then I'm going to have basically half of pi in terms of radians, or in other words, I'm going to have pi over 2 radiuses to represent 90 degrees. Okay, this 45 degree angle, we've already established that it takes 1 pi in terms of radians to represent 180 degrees, or in other words, it takes 3 and then just a little more radiuses to represent pi. Well, it takes a fourth of that to represent 45 degrees. Or in other words, if I just take a fourth of my radius, I can put it right here and it would represent 45 degrees, or a fourth radiuses, or in other words, we use the term radians. Okay, so it might take a little while to get used to, but I just want you to think of angles in terms of the number of radiuses it takes to form those angles. And instead of using the word radiuses in a bad way, we use the term radians. How many of these does it take? And it's always in terms of pi, does it take to form an angle? And you're going to get used to seeing angles both in degrees and in terms of radians, like I've shown here, pi over 4. This would be the pi over 4 radians, pi over 2 radians, 3 pi over 4 radians, pi radians. If we keep going all the way around, all the way back, make a complete circle, then we have 2 pi radians. That probably makes sense. If halfway around the circle is 1 pi, then all the way around would be 2 pi. Okay, so let's just go ahead and fill out the rest of the circle. This would be 270 degrees, but what is it in terms of radians? Well, it's 1 pi plus another half pi. So it's like 3 halves pi, or we would say 3 pi over 2 radians. Okay, so now that we've had a brief little discussion on what radians are all about, let me show you a formula to convert from degrees to radians. Okay, and then we're actually going to use this formula on the next slide. So if you're given degrees and you're asked to convert to radians, you're going to multiply, this just means times, you're going to multiply by pi radians over 180 degrees. And I'll show you in the next slide a little trick to make sure you always use the correct conversion factor. If you're going to convert from radians to degrees, you always multiply by 180 degrees over pi radians. You just flip it over. All right, so let's just take a look then. This is what you're going to be doing on 25 through 30. So letter A is given to us in terms of radians. So I'm going to multiply by the conversion factor to change radians into degrees. So I'll just back up again. from radians to degrees, I'm going to multiply by this conversion factor. 180 degrees divided by pi radians. Okay, see how this is the conversion factor. So here is how you can always remember if you're using the right conversion factor. All right, you'll be given either degrees or radians. If you're given radians, this will be some multiple of pi in the numerator. Just look diagonally, and these should cancel each other. Okay, pi radians, those are going to cancel. And what I'm left with is just regular numbers, 180 degrees divided by 4. So if you look diagonally, you should be able to cancel if you're using the right conversion factor. All right, my pi here cancels. So I'm going to grab the calculator, and you don't need to enter degrees. You just need to, in your calculator, to enter 180 divided by 4. And we've looked at this already. That's 45 degrees. And we illustrated that here. 45 degrees is the same thing as pi over 4, or 1/4 pi radians. Okay, so that would be my answer for letter A. Letter B. This is given in degrees, so I'm going to use the conversion factor to change degrees to radians, and notice it's just the opposite. And you can always know that you're using the right thing because, once again, if I look diagonally, I should have the same type of unit. Okay, so I can always cancel going this way. I can find something to divide into that would cancel or reduce these 2 degrees. All right, so going this way diagonally, they were both in terms of pi. I could cancel. Same thing here. I can cancel going diagonally this way. All right. So let's see if we can find something that will divide, something that divides both into 180 and 225. And 225 and 180 are both divisible by 45. Okay, and usually you should be on the lookout. The most common way of dividing or canceling is dividing either by 30, 45, or 60 degrees. So be on the lookout for those. Those are pretty common ways to reduce, either 30, 45, or 60. There may be others, but I would start with those. All right, so 225 divided by 45 should be 5. So here I'm canceling, dividing by 45. Okay, this is 5. And then I'm going to divide 180 also by 45. And that's 4. Okay, so I've converted now. Again, when I convert from degrees to radians, I'm not going to use degrees. I've just divided by, think of 45 degrees into each one of these. And my final answer is going to be 5 pi over 4 radians. And it's understood to be radians when it's written as a multiple of pi here, so you don't have to write the word radians. So that would be my answer for letter B. Okay, letter C is given in terms of radians, so I'm going to convert it to degrees. So it's going to be just like we did up here. I'm going to multiply by 180 degrees over pi radians. You can check yourself and make sure you use the right conversion factor. If you look diagonally, they should match. You should be able to cancel. The pi's are going to cancel. You could also cancel this way if possible. So here we go. We can just use our calculator at this point. If I do -3 times 180, -3 times 180 is -540 degrees divided by 8. And so if I do -540 divided by 8, I got -67.5 degrees. Okay, so for letter D, I'm given degrees and I'm supposed to convert to radians. So once again, think of your conversion factor just like we did in letter B. Just keep in mind that if you go diagonally, degrees and degrees, they should match. So when you go diagonally, those should be the same. Here it was radians, radians, diagonally. Degrees, degrees. So my numerator here is going to be pi radians. So once again, I'm looking for a way of reducing to get my answer. You could divide by 20 degrees in this case. 20 goes into negative 40, of course negative 2, and 20 degrees goes into 189, and so we multiply this all together and we get negative 2 pi over 9. Radians will always be represented as a multiple of pi. All right, letter E is in terms of radians, so I'm going to convert it to degrees. And so I use my conversion factor 180 degrees over pi radians. Just double check, look diagonally, they're the same units, pi and pi. So the pi's cancel. I can reduce going this way. I can divide 2 into itself, 2 into 180 degrees, that's 90 degrees, and 90 degrees times 5 is 450 degrees. Okay, and one more, and we're converting degrees to radians, so once again, make sure that degrees are opposite diagonally from each other. And so we'll put pi radians as the numerator. And it's always helpful to cancel if you can. 60 degrees goes into both of these. 60 degrees goes into 120 degrees twice. 60 degrees here would go 3 times, and that's not too bad. We have 2 pi over 3. All right, and so you've had a little taste of converting from radians to degrees and from degrees to radians, and hopefully you'll get a lot of practice with these two conversion factors. And I hope you understand a little bit more what we mean by radians. How many radiuses does it take to form the outer arc of the angle represented in degrees? Okay, this is it. Your last few problems will actually be using a formula that I'm going to give you to find the length of this arc. How long is it? Not the degree of the angle represented, but how long actually is this arc on the circle that is being subtended, that's the official math term, subtended by this particular angle. So we're going to be interested in finding out the distance of this outer edge, this arc that's represented by the creation of this angle. So it's a pretty simple formula. It's the radius of the circle, which you will be able to tell, okay? The radius of the circle, noted by R, times the measure of the angle, and this is the Greek symbol for theta. It's a popular way of representing angles in math textbooks. So theta always has to be in terms of radians in order to use this formula. So if you happen to be given this angle measurement in terms of degrees, you'll need to do a conversion into radians first before you can use this formula. Okay, so let's just take letter A for example. I'm after this arc length. How long is it from here to here? The angle is given. The angle is pi over 6, and the radius is 2 inches. So to find the arc length, called S in this formula, I take the radius, which is 2, and I multiply by the degree measure of the angle, which in this case is pi over 6, and you can do some canceling, or you can just go ahead and multiply together and reduce. You get 2 pi over 6, which is pi over 3, and we're rounding to the nearest tenth, so you need to grab your calculator and in your calculator you're just going to hit the pi button. So you're literally going to do pi, and pi is right below the natural log button, and then do divided by 3, and that's a pretty long decimal, 1.0471975551. We're just supposed to round to the nearest tenth, so I'm just going to say it's 1.0 inches. Since our radius is given in inches, we'll use the same measurement for the length of that arc, 1.0 inches. Okay, let's try another one of those. Same formula. If you want to know the arc length, and the formula uses S to denote the length of this arc, how long is it in terms of meters in this case, from here to here. So we take R, which is the radius, that's 13, times the angle measurement, that's given here as 11 pi over 9. And so you can basically use your calculator and multiply these together. So it's going to be 13 times pi, 13 pi, and then divided by 9. 13 pi divided by 9. And hopefully you got 4.5378, but we're supposed to round to the nearest tenth. So that would be 4.5 meters. Okay, so that's it. That is the formula. And anytime we want to find the arc length, we have to know the measurement in radians, and we have to know the radius. And if we know those two things, multiplying them together, pretty simple, will give us the length of that arc of the circle being formed by this angle subtending the circle. All right, so there you have it. That should prepare you for this assignment. And if you have any questions, let me know.